Okay, everybody, nice to see you all. Um, Sorry to start a minute late. I'm afraid the previous instructor took forever to get out of the room, and our TAs are apparently not here. So let's see here. In order to get started, you have a homework. I believe it's due this Friday. Is that right? So you should probably start that if you haven't already. It basically covers the last little segment of this course. Notice that you are still responsible for the contents of these lectures beyond the end of the last homework, all the way through the very last lecture for the final exam, which you guys have now made like an NP-hard scheduling problem to actually figure out a date for the makeup for this exam. So we're currently figuring that out, but hopefully by the end of today or tomorrow, we'll just choose the date, and then you guys will have to deal with it. Aha, there's our TA. So right, so that's the main thing. Do work on your homework. You do have late days for this course, but beyond the however many late days plus the additive amount of points that get removed after that, then you're done with your homework. Any questions, comments, concerns about logistical stuff? Cool. All right. So today we're going to embark on sort of the final theme of topics in this class, which is another fun one. This is one of my favorites, which is studying the numerical solution of ordinary differential equations, or ODEs. Now, I think in a typical numerical analysis class, this topic comes a lot earlier. But in this particular course, I decided to reshuffle things for a few reasons. One is that the elementary theory of ODE is really boring, and so if like you just do it at the beginning of one of these courses, that's kind of as far as you can get because you don't have the numerical tools you need to do the really advanced stuff. And moreover, my experience in computer science is that actually relatively few of you guys are actually solving ordinary differential equation relative to the many of you that are solving optimization problems day to day. So this class is flipped a little bit backward from like most textbooks that you see in the domain. But what we're going to see is there's a lot of really beautiful links between these two areas that allow us to use the tools we've already developed in this class to make for nice ODE solvers, and vice versa, in particular to use ODE solvers, we'll see today, to propose new optimization algorithms. So there's sort of a nice back and forth duality kind of thing that happens here. Now, my understanding is that MIT technically does not require a course in ordinary differential equation among its undergrad, although it does require like 2 physics and like 1,000 biology classes. I'm on the committee for battling over undergrad curricula at the moment, which is an interesting experience in MIT politics. But in any event, just so that I know, this is a judgment-free zone, to use the language of, I don't know, isn't that like it's like a crappy gym in Porter Square? Have we encountered an ordinary differential equation before in our life? It's okay if we haven't. We're going to review the basics. Okay, so many of you guys have at least seen some version of that, and even if you haven't, we'll do a quick review. And something that's worth noting is that the textbook has a pretty comprehensive set of examples and very kind of basic theory in case you haven't seen it before. I think it's interesting that our pure math students haven't seen this stuff. Okay, so right, so as we know, the theme of our last couple weeks has been a set of problems in numerical methods where the unknown variable is not just like a vector of values, but rather an entire function, right? And so, for example, we started by talking about interpolation problems, where our unknown is a function that interpolates between some finite set of samples. And then in our previous 2 lectures, we talked about problems in quadrature and differentiation, which of course extend the basic reasoning from interpolation problems. But I'm going to double check that our recording is actually doing anything. Yep. Today, we're going to put a new twist on our problem, which is we're going to talk about problems where still the object that we don't know is a function or its derivative or integral. But rather than just like having samples from that function, instead we're going to know some property of that function, and we're trying to find the thing that satisfies it. Right? And the most common example of such a problem is an ordinary differential equation. But there actually exist other problems out there that have a similar flavor. For example, integral equations and all kinds of fun topics in variational calculus that this course is not going to be able to touch. Now, there's no shortage of problems that appear in this domain. So for example, if we think about our interpolation problems from before, we could imagine a version where we say not only do we want to interpolate our data, but we also want to denoise it, in which case maybe we have an objective term that inputs the function and outputs some notion of how noisy or messy it is. right? This is an objective term that acts on a function in this particular case. So for example, a very common one in my research domain, if I have a function of one variable, is to look at a quantity, which is like the integral of f prime of t dt. I guess I didn't need to write a norm if it's in one dimension. Which if you think about it, like if I have a function that's like wiggling around a lot, right, then it's got a lot of f prime, and somehow feels like less desirable than maybe an interpolant that's more flat. But we don't really have optimization tools for talking about problems like this because our unknown is a function instead of just a set of values. And it turns out that the tools we'll talk about in the next couple lectures are applicable to problems like this, although it require a bit of legwork to actually link the two together. My goal was by the last lecture of this course to actually do a little bit of that legwork and to talk about a popular research paper in the machine learning domain called Neural ODE, which includes basically how you might backpropagate through one of these ODE solvers, but I'm not sure if we'll actually get there or not because we're a little behind in this class. The more classical example problems that I think are typically used to motivate ODE problems come from physics and dynamics. Probably the most famous ordinary differential equation out there is F equals ma, which is one of Newton's laws, second, third, fifth, second. Which essentially, if you think about it, it gives you some property of the time derivative of the dynamics of your physics problem. And basically, the whole point is that you can use that to resolve the actual motion, right? And so really all F equals ma is just an ODE problem. In undergrad physics, you spend a lot of time deriving kind of special cases you can solve by hand, but the reality is the vast majority of problems in that domain just don't admit a closed form solution, and you need techniques like what we'll talk about here to just visualize and measure things from your model. And then finally, maybe we can work on approximation problems, like I have some function I kind of like, but I think it doesn't have some property, I want to project it or whatever. All of these things fall into the category of things that we're going to talk about. Now today specifically, we're going to talk about initial value problems. So the idea here is that you're given some relationship between an unknown function, the values of an unknown function f of t, and all of its derivatives. And moreover, so by the way, here our function inputs t and then outputs a bunch of values, right? So the typical intuition here is that this is a function of time. So think about like a physics problem where you input time and you output the position of a bunch of particles in a vector. And moreover, you're given some function f. Now this notation took me all the way until graduate school to really kind of bond with, like it felt very abstract to me. But hopefully you guys kind of see what's going on here. And we'll do an example just to make sure that this makes sense. You're given some function f which relates, or I guess a function big F which relates little f and its derivatives all together into some fashion. And then you're trying to recover some little f that satisfies this thing for all time, or typically for all time bigger than 0. And typically what you need to solve a problem like this are f and all of its derivatives up to order k minus 1. So for example, for f equals ma, which is a second order ODE, right? There's two derivatives in there for acceleration. You need f and f prime, like the initial pose of your physical system and the initial velocity in order to simulate it moving forward. So let's do a tiny example of what this looks like. So for example, by the way, I think what we're used to writing is to kind of isolate the highest order derivative on the left-hand side of this problem, but strictly speaking, that's not necessary. And in fact, in this course, we've already talked about machinery for doing that, namely root finding problems. So we can use these slightly more fancy versions of this thing. So for example, I don't know, here's a random made-up ODE that I put in my notes this morning. So here, y is going to be a function of time. By the way, in this lecture, we're going to use prime to denote derivative with respect to t. Okay. So in this case, what would be this capital F function? So notice that we have a second order ODE, right? Because there's two derivatives here. And here's the kind of abstraction or leap of faith that I think is a little bit hard to think about if you haven't seen it before, is that this function big F, it's sort of a function that just has a bunch of inputs and outputs a number. This has nothing to do with dynamics of your problem, or it sort of determines them, but indirectly. So for example, here, maybe I have t, a, b, c, and let's see, what would you get out of this ODE? So we have t, we got a y prime, which I guess would be b, cosine A plus C. Does that make sense? Yes. Yeah, in some sense, like this is an implicit relationship between our unknown functions and its derivative. But the thing, the slight mathematical abstraction here that's worth noting is that like this is just the thing that inputs four numbers and outputs a number. It has nothing to do with time or dynamics or ODE or differential equation. It's just a function of four variables, right? But we can use it in addition to this definition on the screen to kind of give ourselves some nice language for talking about differential equations. Incidentally, we won't get to this in this course. I just had a piece of chalk. But like partial differential equation, this language is also very common. So for example, if you have some unknown function of f of xy, maybe you have, you know, some like x, y, you know, df, dx, df, dy, d squared, f, dx squared, d squared, f, dx, dy, so on. So like this is like a useful abstraction to kind of get used to because in higher level of mathematics, this is a very, very typical thing. Just sort of a footnote there. Or if you take a course on variational calculus, which everybody should do before they die, then this notation is also used, but then it sits inside of an integral. Okay, right, so I guess we did some, oops, I didn't do exactly the same example, but I did up to a minus sign on the board here, but hopefully you guys get the pattern, okay? Now, typically, we're going to see that we like to write ODE in sort of a standard form where you isolate the highest order derivative on the left-hand side. Notice that at least locally, you can always do that by using a root finding problem on capital F, right? You can kind of pull out one of those variables, solve for y double prime. Okay, so the world's most famous example of an ordinary differential equation is F equals ma. If we want to kind of get a little bit closer to the notation that we like in this class, notice that very typically the forces in your physical system depend on three things. They can depend on time, position, and velocity of your particles. So as an example of a force that depends on position, of course, if I have two particles in my physical system and I connect them with a spring, the farther apart the particles are, the larger the force is, right? Can anybody give me an example of a force that depends on velocity? Damping, yeah, or drag, right? So for example, if I drop a textbook out of an airplane, eventually it reaches some terminal velocity, which basically, the reason that happens is because the force that you get from drag, like as you're falling down in the wind, is kind of proportional to velocity, but in the other direction. So the faster you move, the more it's kind of pushing back. Yep. Can force depend on acceleration? No. And in fact, in some sense, that's an understanding of Newton's second law, is that basically his point is that the motion of your system is determined by things that only know about position and velocity, right? I mean, in some sense, that was Newton's big observation. One thing that's worth noting, just as sort of a mathematical formalism, is that our vector x does not need to be in 3D. In particular, if we really want to think about Newton's laws mathematically, x should contain all the positions of all the particles in our system, right? So for example, if I have 100 particles, then I should have 300 element vector as our unknown x of t, right? For the x, y, and z position of every particle. Make sense? We're going to start out pretty easy in today's lecture, and then we're going to like jump up 8 orders of magnitude of difficulty in our next one. We talk about numeric integration. Okay, so this is sort of the most famous motivating example for ordinary differential equation, and I think if you take a classical numerical analysis class, you basically stop here. But the reality is that differential equations are everywhere in modeling. Another very typical one, which I guess really is somehow an extension of Newton's laws, appears in protein folding. So let's say that I know, which these days often we do, all of the atoms or molecules that make up a given protein. These are very complicated objects and the molecular scale. Then a very challenging problem numerically is to predict the conformation of all of those atoms in 3 space. And actually this is at least for many models of protein folding, I'm sure there are other ones that account for quantum effects and so on, but the basic model of protein folding really is just kind of a Newtonian dynamics problem, where you have between every pair of atoms in your protein, you have some forces that depend on position, right? So for example, there's a very famous model, I think it's called the 612 potential, which kind of looks like that, where like atoms want to be at some distance that's not too far away or too close. But if you push the atoms too close together, then the potential energy blows up, and then they like push back really, really hard. And as atoms move farther apart, they kind of draw into each other, but just a little bit. But anyway, there's all kinds of complicated force models out there. The big annoyance in protein folding is that some of the forces are really, really, really strong, and some of them are really weak. Right? So for example, like there's certain like types of bonds that you probably learned about in chemistry class. If you're wondering, I have no expertise in this topic at all, so there's high likelihood that what I'm saying is false. The bonds that you learn about in kind of undergrad high school chemistry class are quite strong, right? They really want the molecules or the atoms to sit at a particular distance from one another. Whereas there's other sort of weaker forces, for example, the tail end of this kind of potential here. And here's the annoyance of protein folding, is that the weaker forces are the ones that are making the sort of high level motion and shape of your protein. But sadly, when you do your physics simulation, all of these little individual pairs of atoms are vibrating at this very fast rate because they're like bouncing back and forth in this little tiny potential well there. And so unfortunately for us, the time step, like the t's that I need to resolve the motion, have to be able to resolve this high frequency wiggling back and forth, which is sort of a limiting factor in simulating these things. And then what happens is you need billions and trillions of time steps to resolve this big slow motion that's happening while everything is wiggling at a really, really fast rate. Yeah, and so in some sense, that's the sort of classical perspective on why protein simulation is really difficult. And because of that, people have thrown all kinds of crazy computational tools at this problem. Everything from just really, really fancy numerical integrators. These days, of course, machine learning is involved, at least for kind of predicting the conformation at the sort of lowest energy level. There are even some really creative ones. I remember when I was in graduate school, there was this really popular, weird idea to make a video game out of this stuff, where you like kind of present people with shapes of proteins, and then like the score in the video game was the potential energy. And apparently that was the state-of-the-art optimization tool for a while, because I don't know, it's a hard problem. But all this is to say that these dynamics are really quite challenging. There's also other applications of sort of solving differential equations that you guys have actually already seen. So let me give you an example. Sadly for you, we are not done with optimization in this course. We never are. Let's say that I have some problem where I want to minimize a function e of x with respect to x. Well, we've actually already covered like too many algorithms for this particular problem, but I would say probably the simplest one is a very simple iteration, right? It says that xi plus 1 is just xi minus some h times grad e evaluated at xi, like that. Anybody want to remind us what this algorithm is called? Anders, help me out. Oh my gosh, you guys are killing me. A little louder. Make sure that Leticia can hear. Thank you. Okay, so you guys are awfully quiet today. That's right. So here's our iteration. Now here's a kind of fun thing that I can do. Let me rearrange this expression ever so slightly. In particular, let's say I write xi plus 1 minus xi divided by h. If you think about it, that's minus grad e of xi. Right, all I did was rearrange the terms in this expression. What does the left-hand side kind of look like, thinking back to our previous lecture? Yeah, this looks like a derivative, right? So in some sense, what we accidentally did was made a computational model for solving a particular ordinary differential equation. This is dx dt is equal to minus grad of your energy x. So there's actually a really nice duality here between optimization algorithms and solving differential equations. Namely, as you take a limit, as your learning rate, your step size, whatever, for gradient descent goes to 0, what you recover is actually a smoothly varying function of time. Now, beyond being a fun fact, this is actually a nice procedure for deriving new optimization algorithms, A, and actually understanding properties of the optimization algorithms that we already know. So for example, in this class, we already have kind of figured out gradient descent works okay, but if you take steps that are too large, it can blow up, right? And what we're going to see today is that this formula here, which we're going to call forward Euler integration, has exactly the same property. But when we're using, and that property extends not only for optimization, but also for doing things like solving Newton's laws, right? So there's a really beautiful duality between optimization and differential equations that are really clean. And moreover, this gives a nice way to derive new algorithms. So for example, one thing you could do is say like, well, if I kind of think of this as a discretization of this differential equation, there's a reasonable question, which is why do I evaluate grad E at time I and not I plus 1, right? And we're going to talk about this more at the end of today's lecture, but we could define a different ODE integrator, which basically does the following: minus xi over h equals minus grad E at xi plus 1, like that. That's a I plus 1, yikes. Now, this is a system of equations to solve for xi plus 1, right? It appears on both sides. But I could solve it to get xi plus 1. And when I do that, the strategy for solving differential equations is called backward Euler integration. We'll talk about that more in today's lecture, for sure. This is just kind of a preview. But the thing that I want to emphasize, does anybody recognize this expression from our optimization lecture? This is so much fun. I love this stuff. Let's rearrange this expression a little bit. In particular, now it's not so easy to, yeah, okay. Actually, before I think too hard, let's just rearrange this expression. By the way, I'm doing this off the top of my head because I didn't know I wanted to talk about this, but now I kind of do. I'm invested. Okay, so let's solve this thing by isolating a 0 on one side. So in particular, we will get xi minus xi plus 1, like that. I guess minus h grad E xi plus 1. Cool? I don't think we've done anything too exciting. Okay. Now, here's a kind of fun thing. This thing is very clearly the gradient of a function. Yeah. I claim this thing also is the gradient of a function, if we think about it. In fact, just for fun, let's flip the sign of this entire expression. So we're going to have plus, plus, minus. Clearly I can do that. Just multiply both sides by minus 1. Maybe I have an idea what I'm going to do. This is such a fun observation. Here's what we can do. This, I claim, is the gradient, I guess with respect to xi plus 1, in some sense, of a particular expression. Like that, plus he, like that. You guys see I'm kind of reverse engineering an expression here? Does everybody see how I got from here to here? I think if you read it in the reverse order, you would probably be more comfortable with that by the calculations we're doing in this class. Does anybody remember this thing is called up to a factor of h? We talked about this a few lectures ago. Yeah. This is a proximal operator. Yeah. So in fact, this is another optimization algorithm. Notice, what is this thing doing? Like in some sense, it is trying to minimize some weighted sum of our energy and a distance term, which we defined a couple lectures ago as just a proximal operator, as sort of an alternative to gradient descent. Right? So in fact, a lot of the different algorithms that we have for optimization really can be derived directly from solving ordinary differential equation and then reverse engineering an optimization form or vice versa. Yeah, so there's a really beautiful duality here. Because of course, what does this mean? That means if we wanted to solve this, that is equivalent to minimizing this expression with respect to xi plus 1. Yes, Ernst?
Is it a problem that it's going backwards here to some extent? Like
it's called backward Euler, in fact.
Operator, like you have whether you have x plus 1 or xi plus 1 or just xi.
Well, you have to be careful. So basically, what do we know and what do we not know when we're solving this differential equation? We know xi and we don't know xi plus 1, right? So this is just a constant. Yeah, so there's no problem here. It's just kind of an annoyance. Yeah. So in particular, a different way to write this expression is that xi plus 1 is really the argmin over x of, I think usually you put the h on the other term. So 1 over 2h of x minus xi squared plus e of s. Yeah. And that's exactly the prox operator we wrote before. Right? So in fact, we can think of that prox operator from before as basically solving an optimization problem, or equivalently as solving a differential equation problem. And in fact, what we're going to see in today's lecture, this particular integrator is called backward Euler integration, and it is unconditionally stable, meaning that it never blows up. Right? So h can be really, really, really big, and backward Euler never blows up. And in fact, there's also a theorem about proximal optimization algorithm, which is that unlike gradient descent, you can take an arbitrarily large h, and it'll still converge. Right? And so there's actually duality in this case between optimization theory and differential equation. Oh, my mom's calling. Okay. Right, so in any event, I'm getting ahead of myself because I think this is just so much fun. But basically, my point is that there really is this nice pairing between all the topics we've talked about so far in this class. And it's really elegant. And you can use the theory for one of these to talk about the other. That a lot of optimization techniques really can be understood as discretizations of a pretty simple differential equation, and vice versa. A lot of differential equations actually secretly are solving optimization problems. Your TA Leticia, for example, published a paper last summer that shows that for particular problems in elastodynamics. Okay. In case you're not convinced enough that differential equations are important, there's so many other domains. Another one that is close to my heart, because I used to work in a movie studio, is in crowd simulation. So here, your vector x is probably like the positions and poses of all the different characters in your video game or your movie. And there's actually these fascinating phenomena that at some scale, like if you zoom out far enough and there's enough humans moving around, they start to behave a little bit like a weird continuum object. Right? And so you can actually write the same way that we have physical laws for determining relationships between particles in physics and molecules and so on. There's also like shockingly replicable laws for how humans tend to interact. Like if we're talking to each other, there's a particular distance we like to stand at and a particular angle and so on. And there actually is a huge literature out there that basically tries to codify all of those laws in differential equation language and then use them to simulate huge crowds. And in fact, a lot of the state-of-the-art tools, for example, I think we use it a lot, especially in zombie movies, because there the motion can look a little unnatural and it's fine, really are using differential equation solvers behind the scenes. In addition to movie effects, one of the places that these differential equations shows up very commonly is in public safety. So for example, if I'm designing a stadium, I think is the very typical example. Stadiums are kind of interesting buildings because they pack tons of people in them to go, watch your favorite football game. American football, to be clear. And you put all of these people in this space, but if you think about like even Fenway in Boston, the number of exits is really not that large relative to the number of people that are packed into this space. And so what can happen is if there's an emergency right in the center of your stadium, suddenly everybody gets up and they want to leave, and there's this dynamical problem where they're all being squeezed through this small interface, and they're all trying to basically, at that point, probably their brains are operating on a pretty base level, but it really does end up looking a lot like a differential equation. And in fact, people use these models to evaluate safety of architectural structures to make sure that in these emergency situations, the dynamics of people moving around are not going to cause a bottleneck or a problem, and that egress is a reasonable thing. Yeah? So it's kind of interesting. It's actually very similar models on both sides. Incidentally, there's all kinds of fun links to other research disciplines hiding in this particular example. One of my favorite, actually, there's beautiful psychological studies that are trying to figure out exactly what the differential equations are that govern motion of people in a given space. And there's so much fun. There's I should dig it up. If you remind me, I'll try to find it. There's a SIGGRAPH paper from a few years ago that did basically psychological experiments to try to understand, like, if I wanted to make video game characters that are not super important, so they're just like following physical looking laws, how should I make their motion kind of modeled in a way that doesn't feel uncomfortable? And so they did all these funny experiments where they like engineered hallways of different widths, and they had people walk past each other and kind of determine like the path. Like, obviously you don't want to bump elbows, so you tend to like rotate a particular angle, but like if you walk past somebody and you like rotate and then you like shuffle and then you rotate again, it looks really terrible. And there's a directionality to it. Like if you face the wall, I think it just feels uncomfortable, even though like geometrically speaking, it's perfectly fine. And so anyway, there are these really uncomfortable videos where they did all these human experiments where they just like showed people videos with different parameters in these models, like how much do you turn when you have relative body sizes and so on. Um, and they're really fun examples because it like really tests your like weird human instinct brain where it's completely irrational, but like some of these just look terrible. And the applications make perfect sense because when you're making video game characters, you want it to look natural, and so they need to understand these like weird dynamical laws that are underlying all the things that we're doing. Anyway, fun fact. So all this is to say, there are so many differential equations out there in the world that it's worth studying in this course and just in life in general. Okay. Now, we're going to dig a little bit into ODE theory. This is not a course on theoretical ODE and existence and uniqueness and so on. The good news is that ODE theory is extremely broad. By the way, when I say ODE, I mean ordinary differential equation, which is the term for I have an unknown function which is of one variable like time. This is in contrast to partial differential equation where there are multiple independent variables like x and y. Okay, so here's some examples of ordinary differential equations just written in closed form. All of these things are of varying difficulty. So the very first one, like y prime equals 1 plus cosine of t, notice the right-hand side of that guy has no y dependence, so I could recover y pretty easily by just integrating both sides. But once we stick a y into the equation, now it's no longer obvious what to do. So the simplest one is like something like y prime equals ay, so this would be linear in the unknown. But already, one thing that you should note, like what is the solution of this ODE, by the way? I have y prime equals a times y. Ah, you guys are so slow that we'll just derive it together. Okay, let's write it like this. dy dt equals a times y. So let's divide both sides by y for fun, maybe ignoring the y equals 0 case for now. We get 1 over y dy dt equal to a. And now what can we do? We can integrate both sides with respect to t. Like that. Notice that these dt's cancel, and that's not just a notational thing, they really do, is from the change of variable formula. What's the integral of 1 over y? Yeah, natural log. So in other words, we have natural log of y equals a times t plus just some unknown constant. Yeah. Or the more typical way to write this is, of course, y is equal to maybe a different unknown constant, maybe like a big C times e to the at, like that. Ta-da! I mean, I didn't even look at my notes. Isn't that fun? So essentially the thing to notice is even if our ODE is linear in y, the solution is not, right? There's an exponent hiding there. And of course, things get more complicated from there. You might have time and value dependence. It might be that you have more than one derivative. It might be nonlinear and implicit. So for example, here you have y prime hiding in an exponential. All kinds of weird, crazy things that happen in reality. I think the assumption that we're going to make in this course is that we can write our ODE specifically in a form called explicit form, meaning that you took the highest order derivative and you isolated it on the left-hand side. And one thing you can convince yourself is for almost any reasonable choice of f, locally you can do this using some kind of root finding tool. I'll let you think about that at home. Okay, so like f equals ma is already basically in that form. Any questions so far? Cool. I'm rushing through this a bit because I do think this is hopefully like familiar language and mostly review, but no problem if it's not. Okay, so what we're going to do first is, in some sense, I think very, like a little bit trivial mathematically speaking, but actually indicates to us that we can be pretty lazy when it comes to deriving algorithms in this domain, which is the following. We're going to go through a proof. I don't really need my notes for this, but I do want to make sure my notation lines up. Yeah. As follows, we're going to use a procedure called reduction to first order. It's a great way to manufacture exam problems, incidentally. That shows that actually our ordinary differential equation solvers can be much simpler than we think in terms of like what they actually have to be able to do. So for example, let's say that I have an ODE in the standard form here. And in fact, I think it's actually easier to do an example. And then you guys will see the example generalizes very easily. It's just one of these things that there's like a lot of notation in the generic case and very little if you do an example. All right, so let's say that I have a fun differential equation. So for example, y prime, or double prime rather, is equal to, I don't know, y prime plus t times, I don't know, sine of y. Okay, and our goal, again, is to find y as a function of t. All right, so this is called a second order ODE, because the word order refers to the highest derivative that you see in the expression. But here's kind of a fun thing that I can do. Let's define a new function v of t, which we're just going to define to be equal to y prime of t. I can certainly do that, right? I can do anything I want. Yeah? Okay. So in that particular case, what is v prime, like the first derivative of v in time? Well, if you think about it, that's y double prime, right? Because I can basically differentiate that expression on both sides. But we have an expression for y double prime is equal to y prime plus t sine of y. But wait a second, what's y prime? V, right? So this thing is v plus t sine of y. Everybody see what I did there? Notice that this expression on the right-hand side does not contain any derivatives at all. Yeah? So what did we show? We showed that this second order ODE is actually equivalent to a first order ODE in, I think typically, I always get the order wrong. Yeah, y and then v. So what is y prime? Well, it's equal to v. And what is v prime? It's equal to v plus t sine of y, like that. So you guys see what we did here? We started with a second order problem, and we exchanged order, like number of derivatives, for first order, but 2 variables instead of second order and 1 variable. Yeah? And if you think about it, there's nothing special about this procedure. I can take a generic ODE of the form on the screen here. I'm not going to write it because there's a lot of symbols. And I can always write it in some yucky form like this, meaning that basically, as long as I don't mind my ODE solving for functions with vectorial output, which we should probably do anyway, like most of physics requires more than one one-dimensional particle, then in some sense, there's no need to derive solvers for differential equations of higher order than 1. Does that make sense? Now, to be clear, I see there's no free lunch here. What have we exchanged? We have exchanged the number of derivatives in our problem for the number of variables in our problem. So it might be that this is a good idea. And then in the next 2 lectures, we'll talk about some cases where it's not. So in other words, like, what have I shown? I've shown that if I have a piece of software for solving first order ODE, I can use it to solve higher order ODE by using this reduction. What I have not shown is that that software is necessarily the best solver for second order ODE, right? Like maybe there's some specialized tool that does better. So for example, in physics, I believe the kinds of tools that are popular are like leapfrog integration, symplectic integration, and so on, like things that tend to conserve energy, which is important in physics. And for that to happen, you need a notion of energy, which only happens for a second order ODE. Yeah. Jonah.
If your point in physics, if we're normally not solving over something that is scalar,
Mm-hmm.
are like sort of key equivalent with vector value, do we then get a matrix?
Do you get a matrix? No, to be clear, the right-hand side here is a vector. It's just that its size has increased, right? So think about, in physics, let's say I have 10 particles, right? Then there's sort of 2 different things I could do if I solve F equals ma. I could have a 30-dimensional vector, which is the positions of all the particles as a function of time, right? And then Newton's second law basically is a second order ODE in that thing. Or if I have 10 particles, I could make a 60-dimensional vector, which is the velocities and the positions of all your particles in one thing. And then it becomes a first order ODE in this thing. Does that make sense? Cool. If you guys just do a few examples, like just write down a weird ODE and then reduce it to this form, you'll see it's a very simple pattern. Yeah. Where?
I'm not totally sure that we're relating. Like, are we like codifying those 2 equations in that vector notation?
Yeah. So the idea here is that I have a vector of unknowns as a function of time, y comma v, and that this thing is a this derivative applies to that vector. Yeah, this is good notation to kind of get used to. Any other questions? I'm glad you guys are thinking critically. This is great. Okay. Right. So the textbook includes a few other examples. For example, here's a third order ODE. One thing that you might notice, by the way, is that notice that the only interesting expression when I do this reduction of this form is the very last row, right? All of the other ones, like you see all these ones and zeros in this matrix, are really just expressing the fact that like the derivative of this variable is the next variable, right? Like these are, you're going to have a bunch of really boring things and then one interesting thing at the very end. Okay. Right. So what have we shown? In some sense, this reduction shows that we only really need, in quotation marks, software that can solve a first order ODE like y prime equals f of t comma y, right? And that we here y is vectorial. And as long as we have code that can solve this problem, in fact, we can solve higher order ODE as well. Does that make sense? Basically, by the way, this is a very typical thing to do in a differential equation lecture, is to do a bunch of reductions so that you can make sort of a minimalist set of algorithms, and then say, wait a second, that was a bad idea. If we know some structure in our problem, we can do better than that. Okay. If we're really lazy mathematicians, we might say, well, wait a second. F has two arguments, right? There's a t there. That feels kind of irritating. Maybe we can get rid of that thing too. This is kind of just like mathematical trivia, but that's okay. Does anybody have an idea of how we can, just for fun, we can get rid of t while we're at it? I think, by the way, typical ODE solvers stop at this step of the reduction, but we can actually be even more aggressive. Oops. Ugh, I'm buzzing. Here's a fact. I'm going to write a highly non-trivial piece of mathematics. What is d over dt of t? 1. That's an ordinary differential equation. Yeah? So in particular, notice that, let's say that I have y prime is equal to big F of t comma y, like that, right? We're going to do a weird thing. So t here is our independent variable. That's like the time here. We're going to make a dependent variable which depends on time in a very boring way. Yeah? So let's call, I don't know, let's say s is some new function of time that happens to satisfy the following ODE. Yeah? So now I can do the following. This feels trivial because it is. D over dt of s y is equal to 1 f y comma s. Or oops, the other way around, sorry. Now, if you think about it, technically, this is now an ODE that has no time dependence. Do you see that? This is just some function that inputs two things and outputs two things. Yeah. So in some sense, what we've shown is that it's possible to write every ODE as a first order, time-independent differential equation. By the way, this is sort of the difference between these things, at least in one dimension. So here, these little slopes are like y primes, right? So if you think about it, like if I solve an ODE like this guy, right, y prime is equal to f of ty, what is it saying? It's saying at every t comma y pair, right, y prime is like the slope of my unknown function. So this is a very typical visualization called a slope field. And then our solutions are like little curves that move along in the slope field. And notice that in the time-independent case, there's actually no t dependence, whereas in the time-dependent case, like on the right-hand side, the slopes can depend on the x-axis, or the t-axis. Does everybody understand this visualization? Okay, so right. So that's what we've shown here. This leads us to our final definition, I promise, which is an autonomous ordinary differential equation, which is an equation of the form on the slide, y prime equals f of y. And what we've shown is that basically by taking a non-autonomous higher order ordinary differential equation and basically just introducing more dimensions to our unknown, we can always reduce it to a form that looks like this. Does that make sense? So what does that mean? That means if I have software for solving just this one guy, secretly I have software for solving a bigger class of problems. That's my point, right? Like if you guys take a computational complexity theory class, like a P versus NP thing, then I feel like you do a lot of proofs like this, right? You showed like, if I have software for solving this thing, then I actually have software for solving this thing, right? It's exactly the same argument we just made here. I would argue a lot easier than that. that equation is. Okay. Right. There are so many different ways to visualize differential equations that it's worth just calling out, because these are figures that you're going to see in these domains quite a bit. So far, we've seen one called a slope field, where the horizontal axis is time, the vertical axis is the value of at least a first-order ordinary differential equation. The reality is that I would argue that most differential equations we encounter in our everyday life are actually second order. And so there's actually a very common visualization called phase space. This is physicists' fault, where the horizontal axis is the value of your function, and the vertical axis here is the first derivative of the value of your function. Notice that time is not visualized in this particular plot. Does anybody recognize this plot? Do you know what this is a phase space of? Yeah, a pendulum. Yeah. So here's a differential equation. Here's the way to understand it. Let's say that I have a weight that's hanging off of a piece of string. There's my string. I don't know why I wanted to make it a dotted line. And there's my weight. And moreover, here's the angle of my pendulum, right? Then if you work out F equals ma, what you will find is exactly the differential equation on the bottom of the slide here. Here's a way to think about it. Like, the force due to gravity is big when it's like this way, right? When you think about its effect on theta. And it's actually 0 when the pendulum's hanging straight down, right? So that's where the sign comes from, because the arm of the pendulum is preventing it from getting longer. But in any event, what can we conclude from this diagram? It's kind of fun. So like, if you think about like the little loops on the inside, the idea here is I pull back my pendulum and it swings back and forth, right? So think about what's happening there. The position is going positive and negative, and the velocity is going forward, backward, right? So if I kind of look in this figure, right, it's like moving forward, backward, and the velocity is flipping sign when I do that, right? So that's how to read this plot. And now, at least in ideal physics, if I then take my pendulum and I smack it really hard, eventually something else happens, which just doesn't swing, it just goes in loops, which is what's going on in the top of the plot here. So that's how to read this thing. So there's no t involved in this plot. This is just a very typical physicist thing, because a lot of our differential equations are in second derivatives. Okay, and then finally, another visualization that's worth being aware of is just the traces of your differential equation. So here I have like an ODE that is, oh no, there should be a prime here. Somebody remind me, I'll fix the slides. There's a differential equation in x, y, and z as a function of time. In this case, I just solve it for a bunch of different initial conditions and just plot what it looks like. So here again, in this case, we're not visualizing velocity, we're only visualizing position. Does anybody know what this ordinary differential equation is called? The Lorentz attractor. Yeah. So this is actually one of the very first differential equations that showed up in the world of numerical ODE. In fact, at MIT, I was just reading the history of it last night. As usual, there's a famous man whose name is attached to this ordinary differential equation, and there's a sadly less famous woman who actually coded the numerical integrator that demonstrated all of these figures here. So I encourage you guys to read the history of this thing and think about it critically. But in any event, there's a really interesting case. I believe they just coded forward Euler integration, which is the very first algorithm that we're going to talk about in today's lecture. And they saw these really crazy traces. This is a model that comes from weather stuff. And the traces kind of look like stable orbits. They kind of look like a pendulum. And then every once in a while, they're like flipping to some other orbit. And for a long time, there was basically an open mathematical question, which is this a numerical artifact? Like, is my solver breaking, or is there something really deep here? And it turned out the answer is no, it actually really is the expected behavior of these differential equations. And in fact, these were the very first examples of sort of chaos in the mathematical sense. And in fact, these are really the worst possible examples for solving differential equations because you expect them to be crazy. So like your numerical integrator is sort of guaranteed not to work super well on these problems, turns out. So in any event, a lot of that history happened here in MIT. Shockingly recently, by the way. You think of these integrators and algorithms as like very classical things, because they are. I mean, like Euler integration is named after Euler. He was around a long time ago. But really, like, these tools only became popular because of computers. And so a lot of, there was sort of this big leap in technology from basically people that were doing calculations by hand to predict motion of planets, and then jump forward like 100 or 200 years to like software for doing chaos theory. So really the stuff that we'll talk about in today's lecture has its history in pretty modern applied math. Okay, finally, before we talk about numerical integration, we should make sure our problems are well posed. So in particular, we've talked about how to write an ODE in this nice standard form, like y prime equals f of y. A question that you should all ask is like, do these things have solutions? Like, and for example, you could imagine maybe there's more than one. Like, we don't actually know that there's not, two different solutions to a differential equation that have my same initial conditions or zero solution or whatever. And in fact, I think this often goes by really quickly in undergrad ODE class, because the reality is that differential equation theory is really strong. Like basically almost any ordinary differential equation, spoiler alert, that you encounter in everyday life has a solution, at least for small t. However, there are a lot of caveats to that. So for fun, oh no. Huh. What on earth? Okay. For fun, I thought we would just work through an example together because we're friends. And that example is dy dt is equal to, I don't know, like I was doing this in my notes yesterday and I was like, I don't know why there's a 2 there, but whatever. The 2 is just like to make it a little spicy. Okay. Dy dt is equal to 2y divided by t. So, by the way, if you take an undergraduate level differential equation class, I think you waste about 85% of your lecture time learning tricks that date back to like the 1870s for how to solve these things in closed form. The reality is very few of these tricks are actually useful in real life. In fact, the numerical solvers that we'll talk about in this class are really what those courses should be covering. However, this particular ODE falls into the very small category of things that you can solve by hand. So let's do that. I'll do it without looking at my notes because I'm a proud something. Okay, so if we divide both sides by y here, we're going to get 1 over y dy dt is equal to, I guess, 2 over t for some reason. Again, we're going to just kind of discount y equals 0, which of course a more rigorous proof should not do. And now, you guys see, by the way, there's basically a pattern here. Like if we can isolate y and t in these problems, we can basically always do the trick that we're doing here, which is to now integrate both sides with respect to t, right? Now we have the integral of 1 over y dy dt dt is equal to the integral of 2 over t dt, which we've already said is the natural log, I guess, times 2 of t. Here, remember, we'll think of t as positive, so it's okay not to have absolute value there. And just for fun, using properties of natural log, we can put it as a square there. Yeah. And since we're doing, I guess, what you would call indefinite integrals, we need like a constant. Cool so far? All right. But now, unlike our previous example, we can do the same thing on the left-hand side. Notice that these dt's kind of cancel if we're like sloppy Leibniz mathematicians here. And what do we get? The integral of 1 over y, which is maybe the natural log of the absolute value of y, is equal to natural log of t squared plus a constant. Here, this constant is enough to account for both indefinite integrals. Okay. So, what do we get? Well, we can exponentiate both sides, and we will get that y as a function of t is some constant, maybe big C, times t squared. Right? There's no x anymore because there's a natural log on both sides. Everybody with me so far? This like feels fine. Right? You have to be careful when you read proofs like this. What did we show? We showed if your ODE is that, then your solution takes this form, right? But like really there's like an if and only if we have to be a little careful about. Now, one thing that we could do is just kind of double check that we actually solved the problem that we set out to solve. Notice that in this case, what is y prime? Well, it's 2ct. So initially that feels fine. Like it does satisfy the ODE. Does anybody notice anything that's wrong? what is y prime of 0? I heard a grunt that sounded like the right answer, but I'm going to wait until somebody speaks up. Undefined, not quite. What happens when I put t equals 0 here? What is 0 times c? Oh my gosh, you guys are killing me. On 3. 1, 2, 3.
0.
Thank you. Okay. Do you see that there's a contradiction here? In general, our definition of ordinary differential equation is that we give it two ingredients. One is the ODE, and the second is the initial condition, like y, maybe y prime of 0 or y of 0. Yeah? By the way, notice, what is y of 0? 0. Do you guys see that that's problematic? I couldn't actually specify my initial condition, right? Because if y of 0 is anything other than 0, I can't solve my ODE. In fact, you can show that that's the case. Moreover, let's say that y of 0 is 0. Is the solution in my ODE unique? No, because any c will satisfy this expression. Yeah. Now, to be absolutely clear, there's like really, I mean, this feels like an okay ODE to solve, but then the more you stare at it, the more it feels uncomfortable. And let's think about it, why that is. Notice that, I mean, what happens in differential equation theory is we specify the initial conditions. Like we specify what happens at t equals 0, and we're using this expression to fill in what happens at t is bigger than 0. There's a slight kind of mathematical technicality here, which is that this expression here does not need to be defined at t equals 0, because I already know what y is at t equals 0. I only need it for all t that are strictly positive, right? However, there is this weird division by t that blows up as t goes to 0, and that's sort of what's going wrong here. And so essentially, what we've shown is that, sure, this ODE is solvable, but with a big caveat on its initial condition, and moreover, if the initial condition falls into the solvable category, you have a non-unique solution. Right? So I think this is sort of the most typical, simple, scary example of what can go wrong in this theory. The good news for us is that this typically does not happen. In particular, here's a very famous theorem, I believe. Is this Picard-Lindelof? I always confuse the names of these things. Which says that suppose our function f here, remember that f is determining the motion of our ODE, is continuous in Lipschitz. At this point, we've seen Lipschitz a few times in this course. Then you have exactly one solution to this thing, and it exists for, in fact, for all time. Is that cool? Incidentally, there's a weaker version of this theory, which says, like, suppose that f is just differentiable but not Lipschitz. Then you can show that you have a solution for a finite period of time, or like there's some little open interval of t around 0 where that exists. In fact, that's actually just a byproduct of this theory, right? Because like, if you just chop off t, then now your function sort of looks Lipschitz because you just like bounded it in some region. So really, this is the hard statement to prove. By the way, fun fact, if you read the proof of this theorem, it actually suggests a whole class of numerical integrators for this problem, because really the theorem basically is like kind of discretizing the ODE and showing that the limit exists and is a nice smooth function. Any questions so far? This is basically just to say that like, if you use these solvers, you do have to be the tiniest bit careful to make sure your problem actually has a solution, but only a little careful, because most problems do. Okay. Yes?
If it doesn't, does your numerical solver just crash?
That's a good question. Yeah, what happens if it doesn't? No, your numerical solver will happily try to solve it. It's just that you can't trust the solution. So for example, you could very easily apply backward Euler, which is the algorithm we'll talk about in a bit, to this problem, and it'll happily do it. But what'll happen is, basically, the algorithms we'll talk about today are going to approximate f at like finite intervals of time. So like one step forward, the next step forward, and so on. And what you'll see is as the intervals go to 0, the solutions that you'll get from your numerical solver just explode. They don't converge to something meaningful. Yeah. Okay. So we're going to talk about one more tiny little piece of theory, and then we're going to talk about algorithms, I promise. And that's basically that a very typical way to compare and understand differential equation solvers is to just look at their action on a very simple equation and kind of understand it there as a model for what can work and what can go wrong in the more general case. And so in particular, what do we tend to do when we're talking about simple stuff in this class is we just throw a Taylor series at our problem and we see what happens there. So in particular, let's say that we're in just one dimension. By the way, this argument works perfectly fine in higher dimensions. I'm just lazy notationally speaking. Let's say that I have a differential equation of the form y prime equals big F of y, where big F is just some crazy nonlinear function, but at least one that satisfies the conditions on the previous slide. And we're trying to understand, at least for like some small t, what this thing looks like. Then a very reasonable thing we might do is to linearize F, which also corresponds to a lot of our ODE solvers anyway, to kind of understand locally what the behavior of this thing should look like. So in particular, we might say, at least for small t, our approximation of y prime is ay plus b for some a and b is a pretty reasonable model to understand locally what's going on in these equations. Okay? And the good news is we can solve this guy. Yeah. And in fact, here's kind of an interesting thing. I've been quite careful here with my Taylor series argument. There's an a and a b here. One thing you guys might notice is that oftentimes we omit the b, which feels wrong, right? Like typically Taylor series needed a constant term. Does anybody know why we're able to do that? Like a little, I feel like there's a lot of mathematical sleights of hand that happen in ODE theory. Here's a little trick. So let's say that I have y prime is equal to ay plus b, and I'm going to define a new variable y bar, which we're just going to define as a shifted version of y. So y, I believe, I'm looking at my notes because I want to make sure I get it right, is y plus b over a. Then notice, what is y bar prime? Well, this is a constant, so it's just y prime, which is equal to ay plus b, like that. And now we can rearrange this expression to get y. So this is y bar minus b over a plus b. You guys see what happens here? Yeah. There's a minus. We got these a's, so actually these two terms cancel. And what you're left with is a y bar. So this is the reason why typically what we call the model equation for ODE, like this kind of simplest possible example, does not include a constant term. Because if you just shift your problem, then the constant term goes away anyway. Make sense? Cool. All right. And by the way, what is y bar of t? Well, we already kind of showed that it's, I guess, c e to the at, where c is your initial condition, right? If you think about it, if you plug in t equals 0, then really you have like y of 0 e to the at. Oh, sorry. Cool. All right. So that's what we call the model equation. It's the world's simplest ordinary differential equation. It has a closed form solution. Does it make sense to use our numerical algorithms to solve this ODE? No, because we have the solution. It's looking right there. This is just a way to understand behavior of our numerical integrators by saying, well, the numerical integrators are not going to recover this formula. They're going to get something kind of close to it. And we can understand their behavior by understanding how good of an approximation of e to the at these algorithms give us. Okay, so this is just a way to kind of understand them. By the way, one thing we haven't talked about very carefully is numerical algorithms for approximating e to the at, right? Your processor has plus minus times divide. It doesn't have an exponent chip. And in fact, you can use ODE integrators to derive approximations of e to the t by kind of reverse engineering the proofs we'll write in today's lecture. Okay, right, so here's our differential equation so far. This is a model equation, super simple. As we can guess, here's what this looks like. I think we've all plotted an exponent before in our life. But now I've included the slope field inside of it. Hopefully I've managed to align those two, which is like weirdly tricky to do in LaTeX. So if a is positive, then our problem blows up. If a is 0, it's constant. And if a is less than 0, we converge to 0. Any questions about this plot? Now here's the thing to notice from perspective of numerical analysis. We talk a lot about well-posedness, like what problems make sense to solve in numerical algorithms. Let's take a look at these 3 plots. Remember that like a well-posed problem is one that's like relatively stable to noise in the input data, right? So like if it turns out I do some tiny amount of rounding, not even in like solving my problem, but just in writing it down, and like my solution blows up, that's like really a problem. So look at the left-hand case. If I get the initial condition wrong of this ODE where a is positive, notice that that error blows up as a gets bigger, or sorry, as time goes to infinity, right? So like if there's some small difference here, and I plot those two curves, they will become farther and farther apart as t increases. And so we typically call these problems ill-posed, right? Or unstable is a different way to put it. Now notice that this notion of stability has nothing to do with our numerical solver. It is the problem itself which is unstable. We're now going to talk about some approximations to this, and what we are going to see is that the notion of stability for an ODE is actually complementary to the notion of stability for an ODE solver, and they're not always the same. Cool? Okay. Right, and so here's an illustration of what that looks like. You know, if A is negative, notice that the distance between the curves gets smaller as you have error in initial condition, and the opposite of true for positive A. Okay. Incidentally, the textbook works through the multidimensional case. It's exactly the same thing. You just do it in one eigenvector direction. In fact, we already did that in our lecture many weeks ago. Okay. So here's basically what we're going to talk about roughly for the rest of this course in some version or another. Is like we're given yk, which is the value of y at some tk. Remember, we're in the autonomous case. We don't need to worry about y prime for now. And now we want to estimate yk plus 1 at some other tk plus 1, assuming that we have access to our function f. By the way, there's a neglected set of integrators that know f and its derivatives, which I would think is worth revisiting in the days of PyTorch. These are called Taylor series integrators. They're worth reading about. They're kind of fun. Maybe make an exam problem. Okay, so the first numerical integrator, which is I think the one that you guys are all likely to have seen in some form or another, or like if I asked you to solve this ODE, probably what you come up with by vibes, does the following. It says, okay, well, if I have dy dt is equal to f of y, then in some sense, in quotation marks, I can say, well, dy is equal to f of y dt. This is quotation marks because, of course, this is meaningless from a mathematical perspective. But it does suggest a very simple algorithm, which is as follows. Essentially, we can just write, okay, so in this case, yk plus 1 is just yk plus maybe h, if that's our time step, times f of yk, like that. This algorithm is called forward Euler integration. It's perfectly reasonable. Okay, notice this is particularly easy to code. Okay. Now, a question we should ask is, like, in addition to vibes, is this actually a useful expression? Now, notice that if we kind of rewrote it, let's rewrite it in a different fashion. F of yk in the ideal universe is really yk prime. But from our previous lecture, we know what? We know that this is yk plus 1 minus yk divided by h plus big O of h. Right? And so if I rearrange this expression here, we get that yk plus 1 is equal to yk plus h times f yk plus big O of h squared. Cool? So this gives us some notion of how accurate our time integrator is as a function of the step, right? Obviously, we want to take big steps, right? Because if we're like trying to predict far in the future, we don't want to use a tiny h because our algorithm is going to take forever. That makes sense? Now, this gives us an error estimate. Here's a counterintuitive thing. What is the order of error for forward Euler integration? Order h. It's not h squared. Anybody have any idea why? This is actually very identical to our discussion of quadrature. Yeah.
Picked up O h squared over from increasing amount of
That's right. So like typically the task that we want to solve in differential equation is not predict the future in a tiny bit of the future. It's like predict the configuration of my system at time 1 or time t, right? And so notice that the number of steps you would need to get to time t is like roughly big T divided by h, right? So the smaller your time step is, the more times you need to iterate this formula. Every time you do that, you incur order h squared error. So you get a factor of 1 over h that kind of appears. So we call this a first order accurate integrator. That make sense? Now, one thing we can do is apply forward Euler to the model equation and see what we get. And let's do that. As usual, I'm talking too much. This classroom is so quiet that I end up saying way more than I usually do when I teach this thing. And we fall behind. Okay, so let's do the model equation. So we have yk plus 1 is equal to yk plus hf of yk, which in this case is just a yk. Cool? So of course we can, and again, we would never do this in real life. This is just a way to understand how our integrator works. Okay? So in particular, notice this is 1 plus ha times yk, like that. Yeah? So in particular, what do we notice? We notice that if we just kind of work inductively, yk is really equal to 1 plus h times a to the k times y0. So for this particular ODE, we can just write down in closed form what our solution looks like. Okay, and maybe because I'm being generous, we're going to assume that a is less than 0 because otherwise, as we talked about before, we really don't have business solving this ODE anyway. Does that make sense? So in some sense, notice, by the way, that this is like roughly an approximation of e to the a t, which I guess is going to be like k times h. Right, we kind of know that because that's the true solution to this ODE. Okay. Now, here's the thing that happens in this problem. So remember that h is negative, or sorry, a is negative and h is positive. Let's say that h is pretty close to 0, right? So then this is like 1 kind of minus a small amount that's less, you know, whose absolute value is less than 1. So some small positive thing. So in that particular case, right, so here we have 0 is less than h is less than 1, right? Then what happens? In every step of integration, we just multiply by a number slightly less than 1. And our function looks like a pretty reasonable exponent. Okay? What could go wrong? By the way, this is again for a less than 0, so there's like a bit of a sign thing you have to think through a bit. Let's say h gets bigger. Yeah.
H gets really big, do we start to get to a point where we're less than -1 and then it just blows up?
Yeah, so in fact, here's a kind of interesting thing. Let's say that I take h big enough that 1 plus ha is actually less than 0. Now, it could be that this value is also greater than -1, right? So that's sort of a medium scale h, right? In that case, notice that your solution actually is still stable, but it does like this weird wiggly thing, right? And then finally, we have 1 plus ha is less than 0 and less than -1, right? In which case, let me rescale my y-axis. What's going to happen? Well, you flip sign, and then you go a little farther than where you started, right? Because the coefficient is in absolute value is bigger than 1. So now you zigzag out of control. Does this look like an exponential? I would argue no. Yeah. So these are these 3 cases. And notice that just like we can talk about stability for the ODE itself, we can also talk about stability for the integrator, right? So in particular, if h is particularly small, here I've actually plugged in particular values. This is not so hard to code. Then we really do get a pretty reasonable solution to our problem. But as our time step gets large, which we might like be greedy and want, like it might be we don't care that approximation quality is so good. We just want something we want to know in the future. Then this integrator, it's not just that it gives us a bad answer, right? That's what our Taylor series argument showed. But it's that it blows up. It doesn't give you a usable answer whatsoever, right? And so that's this idea of stability. And the basic thing that we have shown for the model equation is that forward Euler integration is stable when h is less than 2 over the absolute value of a. Otherwise, it blows up. It amplifies error in the initial condition. This has nothing to do with stability of the ODE itself. Well, obviously, something to do with stability, but mostly is its own notion that there's stability of the differential equation and stability of the solver. Does that make sense? Yeah.
What I don't understand is how you can take that one equation, draw this conclusion, and say, well, this is just the property of this algorithm.
Oh, you're absolutely right. So like if I had a more generic f on the right-hand side, then one thing that you can sort of convince yourself, if you think about it, actually forward Euler is the one case where you can kind of do this. This thing is really just f, right? So think about what's going on in forward Euler. You compute the slope that your ODE wants, and then you just extrapolate it along a line. So in some sense, f and a are kind of equal to each other. And so really the same stability theory is going to apply, right? You don't want to blow up error as you go too far. Yeah. But it's a good point that like the stability theory we'll talk about in this class is specifically for the model equation, and that's to get some intuition. The reality is that there's a deeper theory out there that says if I really care about like very specific f, maybe I can get away with a fancy solver. That's pretty rare, but it can happen. Now, just to introduce you guys to one alternative, and then we'll call it for the day. Here's an integrator called backward Euler. And here what we've done is kind of interesting, and I just want to mention this because this is an idea that's going to show up a lot in our next lecture. This is called an implicit solver, meaning notice that yk plus 1 is on both sides of this equation. This is perfectly fine from a Taylor series perspective, but what it means is that like this isn't a formula for how to get the next yk plus 1. This is a system of equations. But lucky for us, we've talked about root finding in this class, so we have all the tools that we need to solve this kind of thing. For example, Newton's method, Barton's method, whatever. Okay. Now, this is because of that we call this implicit algorithm. It's kind of easy to see the error of this method is the same as forward Euler, right? Because it's kind of just using the same formula. However, let's talk about stability of this thing on the model equation. We're going to go 2 minutes over because sadly we started class kind of late. So in particular, now we have yk plus 1 is equal to yk plus h times ayk plus 1, right? So first of all, notice that this is a system we have to solve for yk plus 1. Even in this case, we have to do a little bit of algebra, right? So here, of course, we have that yk is equal to 1 minus h times a yk plus 1, like that, I believe. Yeah. So in particular, we can conclude from that that yk is really equal to 1 over 1 minus ha to the kth power y0. Cool? And again, remember, we're only going to worry about the stable case, so we're going to assume a is less than 0. Now, if a is less than 0, h is positive, what can we say about this coefficient? Bueller. A is negative, there's a minus sign there. H is positive. The denominator is more than 1, and so the fraction is less than 1. That's right. This expression is always between 0 and 1. Can backward Euler blow up on the model equation? No. I can take an arbitrarily large h, and my solution will always converge to 0. That's what this thing looks like. Okay, so notice that even for giant h, this says nothing about the accuracy of my solver. Accuracy and stability are two completely different notions. However, what it says is I can take really giant steps and we're still okay. And that's sort of the typical example we have of our sort of push-pull in numerical ODE. On the one hand, we can come up with solvers that are very easy to implement and typically are explicit. So for example, forward Euler. We'll talk about some better ones in next lecture. But they typically have what we call a time step restriction, meaning that if h is too big, our solver just blows up, which is no good. On the other hand, we have things that are implicit solvers. They tend to actually be similarly accurate, like as a function of h. So to be absolutely clear, just by switching from forward to backward Euler, we did not get a more accurate solution to our problem. It's exactly the same accuracy. But what we gained is unconditional stability, meaning that if I'm just really aggressive and I want a bad approximation of the future for big future, I can do that with this solver, and at the very least, it won't blow up. And depending on what application you're in, you might want one thing or the other. So for example, if I'm making a video game, then I might be kind of cognizant of the frame rate of my video game, which actually can lead me in either one of these domains, right? So for example, if the ODE that I'm solving my video game is pretty simple and I kind of know what the Lipschitz constant is, I can bound A, all that kind of stuff, then maybe I want to use an explicit solver because it's fast and I don't want this to use up a bunch of computation time. On the other hand, if I'm solving a really complicated physics problem, and moreover, I need a bunch of time steps, then it might make sense to move to the implicit domain. So for example, back in the day, I used to work a lot on cloth solvers, which are very complicated differential equations. It wouldn't be so great if your cloth solver blew up. In fact, my very first job at Pixar was, what's his name, Linguini, running around the kitchen, and his frock was just slowly lifting off, which was not so great. We had to debug the integrator for that. In that case, it turned out conjugate gradient solver for implicit Euler was actually a little bit wrong. In that particular case, maybe what you really value is stability more than accuracy, right? Like animators don't really care if you're solving f equals ma, but they're really frustrated if your shirt blows up. And so it makes sense to move to some other solver like this. Okay. So in any event, in our next lecture, I mean, these are the world's two simplest alternatives. These are the simplest model differential equation solvers. And by the way, the ones that are most common in nature. We're going to talk about a broad variety that give different trade-offs between accuracy and stability. We're going to see that there's a whole host of different things you can do. Moreover, we're going to answer a question that somehow never seems to come up in undergrad ODE class, but I think is really kind of obvious from our lecture. Notice that neither of these solvers we derived actually gets the right answer for the model equation. Right? It gets you an approximation. That's pretty good. But like we have the solution. Here's a question for you guys to think about. Can you cook up a solver for ODE that if I give it the model equation gives me exactly the right answer? These are called exponential integrators. And strangely, they're pretty uncommon. But I think it's worth answering because in some sense, this ODE is so dumb that we would expect our solver to do perfectly on it. We even have the solution in closed form. And yet it's not built into any of the solvers that we have on hand. Okay, so with that, everybody have a delightful rest of your Wednesday. Do not forget your homework. I will see you on Monday. We have one more week of lecture, and then you are free from me forever.